Hi everyone, and welcome to our lab review for Oneway ANOVA. I'm going to be testing out this new software. It's some freeware, so you'll notice the watermark in the bottom right-hand corner. And we're going to do kind of this Khan Academy style review that's supposed to take the place of what I would usually do on an overhead. So I ask that you just bear with me a little bit. I'm going to try to get this done in one take to save some time, and having never used this before, it might be a little bit choppy or sloppy or anything else. But before we get started, I also just want to say that I hope you're all doing well given the situation that we're all in. I hope, first of all, you're all and your families are healthy. And perhaps more importantly right now, I hope that all of you are staying mentally well too. I know with social distancing and social isolation, although it's kind of early into the process for us here in North America, I understand it could really take its toll on some of us either sooner or definitely all of us in due time. So please stay well. Please try to keep your mind busy. Try to connect with people the best you can in whatever way you can. And maybe, I don't know, if we're fortunate, this review is some form of connection to the classroom and some form of connection in the times we have. So I hope you're all doing well, and let's go ahead and get started. So we're going to be talking about ANOVA, and you're probably aware of this by now through lecture or other means, that when we talk about ANOVA, ANOVA is shorthand for the term analysis of variance. So ANOVA, analysis of variance. And we're going to use ANOVA in a very particular context. So I'm going to give it this kind of very broad definition that's not very nuanced, but is just a little bit practical for us. ANOVA is going to be a statistical test we use when we want to compare three or more groups. And when we say groups, we're referring to levels of an independent variable. So maybe it'd be treatment control and treatment at a higher dose, or maybe it'd be treatment group 1, treatment 2 group, and a control group, or whatever, Canada, US, Mexico, something to that effect. And what we're going to see throughout this review, and what you saw in lecture last Thursday, is that analysis of variance is a much different test than the kind that we've seen so far, but it needs to be different in order to overcome the issues of using multiple t-tests. So let's go ahead and get started and kind of hash this out a little bit. So to kind of put some background to all this and give us some context, I want you to just imagine a data set with me. So I'm going to say we have an ID variable. We're going to have a variable called university. And we're going to have a variable that's just going to be our dependent variable. And it doesn't really matter what the dependent variable is in this context. I really just want to illustrate kind of some scheme that we might refer back to as we go through this review. And our sample sizes, I'll also note, are going to be small here just for the sake of demonstration. We would obviously hope they'd be much larger than this. So let's pretend in total we have 15 people. So I'll label them here. Well, I'm going to run out of room. So let's just say we have 12 people instead. And of these 12 people, 4 belong to SFU, 4 belong to UBC, and another 4 belong to Capilano University. So we have, equal representation among these 4 colleges, and then we have their scores on some dependent variable. It could be anything. It could be IQ. It could be their satisfaction with their statistics course. It could be their height, for all we care. But point is we have 3 distinct groups here, and these groups are also independent of one another. So the scores on any group's dependent variable measurements should not in any way affect another group's scores on their measurements at all. So we have a few different ways that we can conceptualize this. The most straightforward way when we think of independent groups is to conceptualize them as separate. So we might say for SFU, we have SFU's sample mean, we have SFU's sample variance, we have SFU's sample size. That is, all of these statistics would be calculated off just SFU's 4 scores here. Likewise, we can think of UBC as having its own sample mean, its own sample variance, UBC, and its own sample size. And likewise, we can think of CAP as having its own sample mean, its own sample variance, or standard deviations if you'd like, and its own sample size. And again, that would be made up of CAP's 4 scores, UBC's would be made up of UBC's 4 scores. So the point is our first scenario we can think of here is that these groups are treated as independent and separate from one another. But we could also imagine a scenario in which the grouping variables didn't really matter much. In other words, we can think of a scenario in which we treated all of these scores as belonging to the same population. I should note, in the first scenario, when we treat these things as separate, so SFU separate from UBC, separate from CAP, we're kind of making an assumption that those separate groups each comes from their own population, just like we did with an independent samples t-test when we said because we treat these groups as independent, we have to assume that they're coming from 2 independent populations. And we noticed when we did the t-test that we didn't distill or combine information about those 2 groups until we calculated that test statistic. Well, here we're going to do this in a kind of different way. We're going to think we can treat these groups as being different from one another, or we can treat them as if at least one group is different from at least one other group, or we can treat them all as if they're coming from the same population. And if they were all coming from the same population, we wouldn't want to calculate different sample statistics per group. If they were all coming from the same population, we'd treat all 12 of these scores just the same in terms of where they come from. So in that instance, we could calculate a sample mean for all of these that we're going to give this subscript G here, and this G stands for grand or grand mean. And we're going to refer to the grand mean as the average of all 12 of these scores together, not separated by group. So this would be comprised of all 12 scores, not 4 scores in isolation like we did for each group. And our ultimate goal is going to be to compare whether it makes more sense to consider these things as coming from a single population, or that at least one of the groups has its own unique population. So moving on, let's talk about why we need to actually do this new type of test in the first place, why we can't just run a bunch of t-tests instead. We saw last week, or maybe the week before, that with 2 separate groups, we only had to make one comparison among those groups, statistically speaking. So to put this into context, imagine we wanted to compare SFU and UBC. To compare these 2 groups, all I need to do is make one comparison between them. And that comparison would be facilitated by use of our independent samples t-test. And when making that one comparison, I'd run one t-test with one alpha rate of 0.05. That means that overall, my total error associated with answering this question, which is significantly different than the other, or significantly greater or less, or are they significantly different, I should say, this gives us about a 5% chance of type 1 error, because we set alpha to 0.05. Now, if I wanted to compare more than 2 groups, let's say if I wanted to compare 3 groups, suddenly the number of comparisons that I have to make starts to balloon a little bit. So with 3 groups, I actually have to make 3 comparisons. And you might ask, okay, if I know how to compare 2 groups, why don't I just repeat this situation among all the groups? So for SFU, UBC, and we'll add cap, again for Capilano. If I wanted to compare these things, why don't I just run 3 separate t-tests to facilitate that, such that I would compare SFU to UBC, UBC to cap, and cap to SFU. The problem with this is with each of these 3 t-tests, we have to consider that each of them is going to have their own alpha. So the comparison between SFU and UBC would have an alpha, presumably, of 0.05. The comparison of SFU to cap would have an alpha of 0.05. And the comparison of cap to UBC would also have an alpha of 0.05. And when we do this, we're just essentially compounding all of that error. So instead of having our regular 5% type 1 error rate, if we were to take this multiple t-test route, we would get around 15% type 1 error rate. And that's problematic because to answer this research question of whether one of these groups is different from at least one other group, having a 15% alpha rate is sky high and wouldn't fly. You can imagine running a single independent group's t-test and setting alpha to 0.15. That would be an incredibly liberal test. It would be incredibly easy to reject a null hypothesis, and that test would not be taken seriously by any other scholar or journal or by your research peers or what have you. It'd be very, very, very problematic. So we run into this error of compounding type 1 error rates if we try to do multiple hypothesis tests to answer this type of question when we're comparing 3 or more groups to one another. We have a specific term for this, and this term is called family-wise error, as in we're running this family of multiple t-tests, and here our family-wise error rate was around 15%. So what does ANOVA do for us then? ANOVA gets us out of the issue of compounding error. And let me go ahead and formalize this on a slide here. And also, apologies, I forgot to mind the watermark, so things still seem legible to my little preview window here, but I'll try to mind that a little bit better going forward. So let me formalize what I just said. We have this ultimate problem. And that problem is using multiple t-tests inflates type 1 error. In other words, we have a very large family-wise error rate. The solution to this problem is then we need to find a way to use a single hypothesis test with a single type 1 error rate. And as you might expect, the test that accomplishes this is ANOVA. So let's dive into ANOVA a little bit and understand why this test is able to answer this research question, is able to compare 3 or more groups in a way that t-tests can't. So we'll start this new subheading as just ANOVA. And here's how it works. The gist of ANOVA, and I'm going to articulate this in the form of just ANOVA's null hypothesis. The null hypothesis is that the 3 population means from the 3 different groups, at least in this example, or however many groups you might have, are all equal to one another. This is what we want to test. The catch with ANOVA And by catch, I mean what makes it different than the kind of means different testing situations we did with our t-tests is that it uses a different type of test statistic called an F ratio or an F-test statistic or just F. This is named after Fisher, who invented this test and also gave us alpha equals 0.05. And what makes this test statistic unique and different from what we've seen before is it's a ratio of variability. More specifically, it's a ratio of what we call between subjects variance to within subjects variance. And I want to really make that clear that this is a ratio of variability. I got cut off here, but again, ratio of variability. So let's take a little step back quickly and talk about our variance terms. In particular, I'm going to talk about our sample variance. So recall that when we're talking about a sample variance, and I'll go ahead and put the equation out here, that our sample variance has a very specific formula. In the numerator, we have the sum of each score minus the sample mean squared over this n minus 1. And these two components have very specific names. The numerator is what we call the sum of squares. The full name is the sum of squared deviations from the mean. So the sum of each score's deviation from the mean, and that total. And the bottom term here is what we call the degrees of freedom. And we could abbreviate these farther as just SS and DF. So when we talk about our variance here, we can think of our variance as being comprised of two terms. All of our variances are going to have a sum of squares and a degrees of freedom. 1, 2. And one more thing, we want to remember that the definition, the conceptual definition of a variance is as an average. In particular, it's the average of the squared deviations from the mean. Just to note, anytime we take the sum of something and divide by the number of things that there are, we're taking an average. Now we talk about like the sample mean as being just the average of the scores, but our variance here is taking the sum of squared deviations divided by the number of deviations there are, in this case -1 to correct for a little bit of bias, but still. So it's like a sample mean, an average. It just happens to be the average of these squared deviations of the mean here. So our sample variance is the average of the squared deviations from the mean, and it consists of these two component parts, our sum of squares and our degrees of freedom. We'll come back to this in just a minute. So, getting back to our situation that we started with way back in our first panel, when we looked at that kind of imaginary data set and we said we can either have all of the scores coming from one population or at least one of the groups being different from one of the other groups. So let's write those two scenarios down. So imagine these two scenarios. One, we treat all participants, or if you like, you can just say all the scores from all the groups, as belonging to one population. And in our second scenario, we can treat the groups as reflecting separate populations, or more in a more nuanced way, at least one group is unique. That is, at least one group comes from a separate population. So looking at these two scenarios, let's look at what they would look like visually. We could have one for the first scenario, we could have one population This population would have all of those means equal to one another. In other words, this kind of reflects the null hypothesis. If we wanted to look at the sample statistics, we could look at the grand mean. So in this instance, that would be the mean of all 12 of those scores. So n equals 12 here. And again, our sample size is limited just because I wanted to make a data set on this tablet, but ideally the sample size would be way larger than this. And this would have a sample variance equal to the sum of each score minus, in this case, the grand mean squared over the total sample size. So, or I guess the total sample size minus 1. So we can think of it as this reflecting our data in the first scenario, or we can think about it in the second scenario as treating each of these groups separate. So we'd have an SFU population, and that would have SFU's population mean. It would have SFU's population variance. It would have only 4 people in it. And its sample mean would be from SFU, scores only. We could have UBC's population with their population mean, and a UBC specific population variance, and a UBC specific sample size again of 4, and a UBC specific sample mean. And we might also have Capilano as having a unique population with its own population mean, its own sample variance of only the CAP scores, its own sample size of only the Capilano scores, also of 4, and its own Capilano sample mean. So what we want to do with an ANOVA is look at which of these two scenarios is most likely. And we're going to do this again using this F-test. And this F-test, again, is different from our independent samples t-test or the z-test or whatever else we've seen, because it uses what we call a ratio of variability. And so we're going to compare what we call the between subjects variability to the within subjects variability. The variability between subjects is going to the variability between subjects refers to the variability of R3 sample means. So this would be the sample means of SFU, UBC, and CAP, respectively. The within subjects variability is going to be the variability in all of our sum of squares terms. So sum of squares for CAP sum of squares for UBC and sum of squares for SFU, or that should be, SFU cap and UBC. Oh man, that should be SFU, UBC, and cap. Excuse me. And so what we're going to do is we're going to find the variability of those sample means and the total variability of each of these distributions independently and create a ratio of those two things. And those two things are going to be used to calculate our F statistic, which we're going to use to ultimately reject or fail to reject the null hypothesis. So let me kind of zoom in on those two things. So we said that the between subjects variability is the variability of our sample means. For SFU, UBC, and CAP. We're going to give this variance term a very special name. It's going to be referred to as the mean square between, or MSB. And when we say mean square here, I want to make sure that we acknowledge that this is a variance term after all. Remember, when we talked about our sample variance just a few minutes ago, we said that it's an average of the sum of squared deviations. So average, mean square, so mean square between. So this mean square between, this MS, is really just a fancy name for a variance. Kind of like we give the standard error this fancy name when it's really a standard deviation of some sampling distribution. It's kind of the same thing happening here. Mean square is a reference to variance. So we're going to calculate a variance term that is based on these three things. And we're also going to calculate a variance term that is based on the total variability of each group's scores. So that would be reflected in their variance terms. Now we're not just going to add these variance terms up, but kind of to make this concept a little bit more clear, I'll just add them here. And the idea is we want to see the ratio of these two things. I'll explain that more in a second, but for now, we're going to refer to this second term as the mean square within, or for short, MSW. So again, this is just a variability term, mean square, this time within, and our F ratio is going to be equal to our mean square between divided by that mean square within. All right, so again, I'll just say mean square is equal to variance. It is effectively a variance. And I can demonstrate that a little bit further for you because, as we said, each variance is going to come with two components. So our degrees of freedoms can also be broken into component parts. My recording stopped, so you might have just heard me say that twice. And it's a lot more straightforward to break down the degrees of freedom than the sum of squares. So you can imagine that we have the degrees of freedom total, and that's going to break down into the degrees of freedom between plus the degrees of freedom within. The degrees of freedom total is pretty straightforward. It is n minus 1, just like we saw all across. So in our example where we had 12 people total across all three groups, this would be 12 minus 1, or 11. That's going to be broken into two parts. One is going to be the degrees of freedom between. The degrees of freedom between is k minus 1, where k is a reference to the number of groups total. So here it's 3, SFU, UBC, and CAP. So it would be 3 minus 1 equal to 2. And I'll just make these pieces stand out a little bit. And that leaves us with the degrees of freedom within. The degrees of freedom within is just n minus k. So in the example that we're using here, that would be 12 minus 3. 12 minus 3 is equal to 9. And so you can see here that the sum of squares total of 11 is equal to the sum of squares between of 2 plus the degrees of freedom total being 11 is equal to the degrees of freedom between being 2 and the degrees of freedom within being 9. Add those together, you get 11. So that was a lot. And if you need to, maybe rewind and watch that again, or at least take a deep breath. But what we've seen between these two slides is one, how to get our sum of squares components for each group, for each piece that we need for our variance ratio or f-test, and the degrees of freedom pieces that we need. And remember, what we're trying to get are these mean square between and this mean square within. So we showed how to get that sum of squares between, that degrees of freedom between, and that sum of squares within, degrees of freedom within. And our F statistic, as I said, is just equal to those two things. Mean squares between over mean squares within. So the last thing I'm going to show you quickly is how to conceptualize this in maybe a more straightforward way. And we're going to just kind of think about what this ratio of variability means to us. So I'm going to show you this graphically. This comes out of the lecture slides as well, but I'm going to break through it. Maybe, I'm not sure how quickly Matt did it, but maybe breaking through it slowly will help. So we're going to imagine we have just a number line here. And on this number line are going to be just values for a dependent variable. So we can call it satisfaction with 210 or something else. Now, if we were to treat all of the scores from coming from one unique population, from a single population, in other words, that scenario 1, let's imagine that the grand mean fell somewhere around here on that number line. Grand mean here. And let's conceptualize that we have these 3 different groups. They have 3 different means, but we want to know if they belong to the same population or not. So let's start with SFU. Let's say that SFU is somewhere around here. Let's pretend that's a normal distribution. Let's say that this is based off of SFU's sample mean. We'll say UBC is somewhere around here. So we have the sample mean for UBC. And let's say that Capilano is down here, based around their sample mean. So ultimately, what we're after here is a ratio of variability of the between subjects variance and the within subjects variance. When we say the sum of squares between, if you remember, that sum of squares between was equal to each sample mean. I'm just going to write this in kind of some simple notation. The sum of each sample mean minus the grand mean squared. So what do these deviations look like? Well, this would be the deviation between SFU's sample mean and the grand mean. So we would square that. Then we would add it to the deviation between UBC's sample mean and the grand mean and square that deviation. And then we would finally add it to the deviation between Capilano's sample mean and the grand mean. So here, that's really only 3 things. So if we take each of these deviations of each of these means from the grand mean and square them, add them all up, that's our sum of squares between. When we talk about our sum of squares within, or mean square within, we're talking about the variability of each of these things. And to make it a little bit more simple, I'm just going to refer to these in terms of their sample variances. And we said that our F-test is a ratio of these two things, kind of the total variability we see among these things and the variability of each sample mean from the grand mean, or the deviation of each sample mean from the grand mean. So you can think of it like this. The farther apart these sample means are from the grand mean, the larger the numerator is going to be in our F ratio. Because the farther apart, or if you like, more variable, these sample means are from the grand mean, the larger our mean square is going to get. And if our numerator gets larger, our whole F ratio gets larger. And if our F ratio gets larger, that means we're more likely to reject the null hypothesis. We're more likely to reject the null hypothesis. So if we were to hold that mean squares within constant, but increase the mean squares between, because our sample means are farther apart from the grand mean, or the variability of our sample means is larger, then we have a better chance of rejecting the null that those three groups all belong to the same population. At least one of those groups might be different. We can also think of this in terms of the within subjects variability. Let's suppose that we held the mean square between constant, or let's suppose that the means that we have here didn't change at all. They were this far apart. If the variance of these distributions were to get larger, let's say UBC's variance was to get larger, and UBC's variance made the distribution kind of fatter like this. Well, if the variability for UBC got larger, there would be more overlap of the UBC distribution with the SFU distribution here. Let's suppose that SFU's also had a variance that increased. If SFU's variance also increased, then there would be more overlap between these two distributions. And if the distributions overlap too much, you begin to wonder why they're separate in the first place. They might have come from different groups, but numerically or statistically, they'd be considered very identical or likely of coming from the same population. And so, as these variances increase, that's going to drive up that mean square within. And it's going to make it harder to reject the null hypothesis, because if this denominator is larger, then the overall value of that ratio is going to go down, right? 1/4 is smaller than 1/2. That 4 is larger than the 2. And so the beauty of this F statistic is that it strikes a balance between how far away the sample means are from the grand mean, or how far away the independent groups are from the situation in which we didn't treat them as independent at all. It strikes a nice balance between that variability and the variability of each group on its own, and whether the distributions here overlap. Remember, the variance is tied to the size of that distribution, or how wide or spread out it is. So as the variance increases, distributions become wider and more apt to overlap, as I've kind of shown here. So I'll return things back to their normal state here. But the general idea is that this F ratio strikes a balance between these two things. And depending on what balance it strikes, we may or may not reject that null hypothesis. And I'll remind you one more time that null hypothesis is that all of these population means are equal to one another. And that actually has an important consequence as well. if we reject the null hypothesis that all the population means are equal to one another, what we're saying is that at least one is different. But there's an important caveat here, and it's that we don't know which one is different. Now, we might be able to eyeball it and say, for example, if the SFU and CAP distributions were like right on top of each other and the UBC distribution was way far away, it might be easy for us to say, okay, well, the UBC distribution is different from CAP and different from SFU. But, the logic here is that if we reject this null hypothesis, all we know is that at least one group is significantly different from at least one other group. And we don't know which. We would have to run some what we call post hoc tests to figure it out. But at the risk of getting redundant, I'm going to repeat this schema just one more time in terms of the F ratio. The F ratio is a ratio of variability, or the F test statistic is a ratio of variability. It strikes a balance between the variability of the sample means from the grand mean. And that's important because the grand mean is the situation in which we consider these groups to be irrelevant and that all the scores come from a single population. So it strikes a balance between the variability of these sample means around that grand mean, and it strikes a balance between the total variability of each group. And again, I've just put the sample mean terms here to reflect that. But that total variability kind of bears on how wide these distributions are and how apt they are to overlap with one another. Because the more these distributions overlap each other, the more likely they are to be from a single population or similar populations, or at least they're very similar, so why would we want to statistically treat them as different? So, depending on the balance that is struck here, this F test might go up and be more likely to reject the null hypothesis, or it might go down and be less likely to reject this null hypothesis. Obviously, we'd hope that the mean square within is lower and that the mean square between is higher if we think that there's evidence to suggest the null hypothesis should be rejected, or if we are trying to, verify or test a hypothesis that some groups are different than others in some respect. Anyways, so that's the end of this review. I guess to recap, I'll just make a couple quick notes here. One is that t-tests, if we run multiple t-tests, lead to inflated type 1 error, which we call family-wise error. And because of this, we have to use ANOVA. And we use ANOVA because it's a single hypothesis test with one error rate. In other words, it only has a single alpha. Now, because we're dealing with multiple groups, we have to change our strategy here. We can't just do the mean differences like we did when we calculated a t statistic or a z statistic. And therefore, ANOVA uses this F statistic, which again is a ratio of between subjects variance using the term mean square between, and within subject variance using the term mean square within. Each of these variances, the between and the within subjects variances, is comprised of two component parts. The mean square between has a sum of squares between and a degrees of freedom between. The mean square within has a sum of squares within and a degrees of freedom within. Each of these parts represents something specific. When we talk about the sum of squares within, that's kind of like the total variability of scores around their sample means. In other words, those variance terms. And when we talk about the sum of squares between, we're talking about the variability of sample means around the grand mean. And then we also talked about our degrees of freedom, but calculating the degrees of freedom is pretty simple. K minus 1 for between, n minus k for within. And so, to recap this F statistic, it's a ratio of variability. Being variances, these each have two component parts, the sum of squares between and the degrees of freedom between, the sum of squares within, the degrees of freedom within. And calculating these two things can be pretty straightforward. And I'll say real quickly also that the sum of squares within is just sum of squares for each group added together. And so ideally, we want less mean squares within values. And if we really think that our groups are different, that is, if we want to reject the null hypothesis, although we should go into things kind of just, interpreting what the data tells us, not with kind of a motivation to reject or not. But overall, that's kind of the gist of ANOVA, that we have to use this variance ratio instead of mean differences testing, and that because we need these two variances, the mean square between and the mean square within, we got to find these kind of four component parts, two sums of squares, two degrees of freedom. And I've shown you here kind of how those two variances strike that balance between whether the distributions overlap compared to how far apart the sample means are from the grand mean. And ultimately, that gets us around this inflated type 1 error problem, and allows us to assess whether multiple groups are different from one another without that issue of inflated type 1 error. Since that ANOVA has just one null hypothesis, one alpha rate, and one decision to reject or fail to reject the null hypothesis. So to close out, I just want to say thank you for bearing with me. I'll be exploring some more variations of how to deliver tutorials. I may stick with this one, I may not, but hopefully you found this review helpful. If you did watch it, I hope it wasn't too confusing. It's a little bit strange kind of just talking to a tablet and not actually reading the faces of people out in the classroom. So please feel free to email me if you have any questions. I'll just remind you that my email address is rhon@sfu.ca. And if you need to, we can also arrange some sort of office hour appointment on Skype or by phone or some other means. So please don't feel intimidated by the way the coursework is going now. Get in touch if you need help or if you need office hour support, and we'll find a way to get it to you. So thank you, and I hope you guys have a good rest of your week. And again, I hope you all are safe and that you are being mindful of your mental health during this time of social isolation and social distancing. So all the best. Take care. Bye.